Okay, in this video we are going to look at something called another delta H. This is the enthalpy of solution. Okay, so right, enthalpy of solution, usually given the abbreviation delta H sol. Okay, this is the enthalpy change occurring when 1 mole of a substance is dissolved in water, and that's to form an infinitely dilute solution. But don't worry about that too much. So delta H sol for dissolving sodium chloride would be this, NaCl solid goes to, and I'll write it as two separate ions, NaAQ and Cl minus AQ. Now we've seen in the previous video that sodium ions are going to be surrounded by water molecules, and the process of water molecules being attracted to them is exothermic, and that's because the water, the oxygen there, is delta positive. And with the chloride ions, you're going to get the opposite thing. So you're going to get the water molecules, the partial positive, and the hydrogen is going to be attracted towards those ions, isn't it? So you can have them that way around. Okay, now let's have a little think about an ionic lattice dissolving. And this always, when I'm teaching year 10s, it always surprises me that usually when you're talking about ionic solids, so you got your ionic lattices, NaCl, is your sodiums. It's a 2D representation of the 3D lattice, okay? Surrounded by chlorides. Those chlorides should be a little bit bigger than the sodiums, and so on, yeah? Now, what do we say about ionic solids? Right, ionic solids in year 10 when you're doing about structure and bonding. They have high melting points, and you explain that because you've got strong electrostatic attractions between the positive sodium ions and the negative chloride ions. So the question is, how come sodium chloride, if you get it and you dissolve it in water, sorry, there should be Na, shouldn't they? Yeah. Well, if you dissolve it in water, you know, the ions miraculously just separate. We just said the strong electrostatic attractions between the ions. So how come it dissolves very easily? You don't have to heat it or anything in water. Well, we now know that you can, if you think of it in two stages, you've got NaCl solid. If we split those up into gaseous ions, okay, Na plus gas and Cl minus gas, that's going to be very endothermic, isn't it? You're going to need a lot of energy for that, to do that. But we now know from the last couple of lessons, when you get sodium ions and chloride ions in aqueous solution, that's exothermic. This is delta H hydration, isn't it? This change here. Some of the delta H hydration of the sodium ions and the chloride ions. And for sodium chloride, delta H sol, right, the enthalpy change occurring when you dissolve 1 mole of the stuff in water is about 0. It's not particularly exo or endothermic. There's hardly any temperature change, and that's because this energy here to break up the lattice enthalpy is almost exactly balanced out by the energy you get out by hydrating the ions. And it also explains why, you know, if you try and dissolve sodium chloride in cyclohexane, something like that, a non-polar solvent. Sodium chloride will not dissolve in cyclohexane, because are you getting these strong interactions between the ions, the strong interactions between the ions and the solvent, the ions and the solvent molecules? In cyclohexane, you're not, because cyclohexane, of course, is not a polar molecule. So you don't get that energy out. So it tends to be insoluble in that. Right, now we need to think about how we're going to calculate delta H sol, and we'll use sodium chloride as the example. Okay, and we're going to do a little Hess's law triangle for that. Okay, and I'm going to start off with gaseous ions on this side here. So we've got Na plus gas and Cl minus gas. Right, and let's make that go to sodium chloride, which is a solid. And down here, I'm going to have not the gaseous ions, but I'm going to have the ions in aqueous solution, so the ions which have been surrounded by water molecules. Okay, now this change, let's have a think about with this change here, what we're doing here. Well, we're forming 1 mole of ionic solid from its gaseous ions, so that's the lattice enthalpy of formation, isn't it? So write that down there. So that's lattice enthalpy, and in that direction it's formation. Let's think what's happening here. We are, 1 minute. Dog wanted to come into the room, so hopefully she won't start barking in a minute. You will hear if she does. Right, so here's, so what we're doing here, sodium, we've got gaseous ions turning into hydrated ions. Okay, so that's going to be the sum of the hydration energies, isn't it? So that's going to be delta H hydration for Na plus and delta H hydration for Cl minus. And then finally, this one here, this is the one that we're really interested in. This is the one we want to find out. Well, we're dissolving 1 mole of solid into the water, so that's going to be delta H sol. And that's what we're going to find out. Now, let's say we were given the lattice enthalpy of formation. The lattice enthalpy of formation of sodium chloride is minus 780 kilojoules per mole. The value for the hydration of sodium is minus 406. Doing a different color. Minus 406 kilojoules for sodium, and minus 378 for chlorine. Okay, so we want to go from here, yeah, to here. So we're going to go the long way around. We're going to do that. Okay, so what is delta H sol equal to? Well, we're going against the lattice enthalpy there. So it's got the lattice enthalpy dissociation effectively, isn't it? So that's going to become a positive. And here, on this bit here, well, we are hydrating the sodium ions, so that's minus 406 and minus 378. And if you do that, what do we get as the answer? That is equal to minus 4 kilojoules per mole. So ever so slightly exothermic. So as I say, not much at all. So when you dissolve salt in water, sodium chloride, you don't notice any temperature change at all. So we're going to use this energy cycle to calculate our lattice enthalpy each time. So just summarize that energy cycle. So let's call it XY. So we're going to have XY. Let's have this gaseous ion, sorry. And that's going to form XY solid. And here we're going to have the aqueous solutions. So we draw right. So this one here is lattice enthalpy of formation. This one here is going to be the sum of the hydration energies. And finally, this one is going to be delta H sol. Okay, so that is the value for sodium chloride. So let's just do a slightly more complicated one. Let's do calcium chloride. So if I get rid of that. Okay, so we're given the data, the following data for calcium chloride then. Calcium chloride, the lattice enthalpy. It's a lot higher than sodium chloride, which was 708 or whatever, and that is because it's the calcium ion is 2 plus, so stronger attraction between the ions, so that's minus 2258 kilojoules per mole. Delta H hydration of calcium ions. Again, that's going to be a lot higher than for sodium ions because they're 2 plus, so they've got a higher they've got a higher charge density. That's 1579 kilojoules per mole. The chloride ion we had before, that was minus 378. But we're going to be a bit careful there because there's 2 of them. And from that, we're going to work out delta H sol. So once more, let's construct the energy cycle, where we're going to have calcium 2 plus gas, 2Cl minus gas goes to the solid, ionic solid. Down here we're going to have the aqueous ions. Okay, so this is our delta H sol. This is what we're going to try and find out. This is the lattice enthalpy, this number up here, isn't it, which is minus 2258 in that direction, the formation. Here we want the hydration. So the hydration of calcium is minus 1579. And then we've got to remember there are 2 chloride ions, so that's 2 times 378. Add up that lot up together, we get minus 2335. We've got to go like this, haven't we? So yeah, we want to go from there to there. That's delta H sol. So we're going the long way around. So delta H sol for this one is going to be equal to minus 2258. Sorry, plus 2258 because we're going against the arrow. Lattice enthalpy dissociation. And then the energy for the hydration, which we've added all up there, which is minus 2335. And that gives us a value for delta H sol. It's going to be exothermic, you can see there. Which is going to be minus 77 kilojoules per mole. And that's enough so that when you dissolve calcium chloride in water, you do notice that it gets pretty warm. Okay, so that is exothermic. And you can see there, why is it exothermic? Well, it's because the energy that you get out from hydrating the ions is a lot more, the energy, well, slightly more anyway, than the energy you have to put in to break up the lattice. Right, now let's have a look at, I'm not going to calculate it because it's pretty easy, but let's think about silver chloride. Okay, so delta H sol for silver chloride, you can calculate it in the same way. And that is equal to, I've got a value here somewhere. Right, plus 54 kilojoules per mole, plus 54 kilojoules per mole. In other words, it's endothermic. And you should be aware, remember, is silver chloride soluble? Well, silver chloride is very insoluble, isn't it? Let's say a test for chloride ions, which we have done in year 12, and he even did it in year 11. Silver chloride is insoluble, and it also, you notice the delta H sol, if you work it out, it's pretty endothermic. Now, if you're looking back on this video after you've done the delta G topic, then you probably understand what's going on here. Let's just see, if you haven't done delta G, so you've not done delta G yet, all I'm going to say is, right, most reactions are exothermic, aren't they? You probably can't think of many endothermic reactions. You can think of loads of exothermic ones. And we'll see, when you've done delta G, you realize why most endothermic reactions can't happen. If you have done delta G and you're reviewing this topic, well, let's just explain what's going on here. So you've got delta G is equal to delta H minus T delta S, which is the entropy, right? And we know this has got to be less than 0, hasn't it? And we know that delta H in this case is positive. So, and delta H tends to be bigger, right? This tends to be a lot bigger than this. T delta S is a lot smaller usually. And the reason why so silver chloride won't dissolve is because of this value here, yeah, the temperature times by the entropy change is not, it's not negative enough to say cancel out or counter that value. Okay, it's not negative enough. Is delta S negative? Let's have a think. Is it negative when you dissolve silver chloride? If you could dissolve it, which you can't, yeah, it would be negative, wouldn't it? It wouldn't be negative. Delta S would be, sorry. Is delta S positive? Is delta S positive? And if delta S is positive, then it tends to make, it makes minus T delta S negative, yeah? Right, delta S is positive, isn't it? Because when you're dissolving silver chloride, you've got an ionic solid, and it's going into aqueous ions, which are free to float around and do their own thing, aren't they? So this is clearly more disordered than the solid ionic, than the ionic solid. However, obviously the increase in entropy is insufficient to overcome the positive value of delta H. So silver chloride is insoluble. That's not always the case. So for example, if you look at some things like thiosulfate, when you make up a solution of sodium thiosulfate, there's sodium thiosulfate, so you've got Na plus ions and you've got thiosulfate ions. When you make up thiosulfate, it is very, the solution goes cold. It's very endothermic. But it can happen because, you know, you're creating, you've got an increase in entropy. So it can happen. And if we relate it to one of those little graphs that we did in the last lesson on delta G, what kind of graph have we got here? So we're going to have delta G on this axis, and we're going to have absolute temperature on this axis. Well, it's endothermic, isn't it? So that means the intercept here is in delta H. That's going to be positive. The gradient is equal to minus delta S. Delta S is positive, so we're going to have a negative gradient. So yeah, look what happens. And you would say, right, delta G at this temperature here, delta G is equal to 0. So that is the minimum temperature at which the solid will dissolve. So yeah, as I say, if you are looking at this video after you've done delta G, you'll understand that. If you haven't done delta G yet, don't worry about that. Just stick with that explanation there. And the main thing is be able to work out delta H sol.